Evaporation-Induced Self-Assembly of Diblock Copolymer Films in Electric Fields, Simulation Insights. This paper investigates how external electric fields influence the self-assembly of asymmetric diblock copolymer films during solvent evaporation, a process known as evaporation-induced self-assembly, or EISA. This question is important because the microstructure orientation and morphology in such films critically impact their functional properties, with direct implications to fields such as membrane fabrication, where uniform, perpendicular cylinder alignment enhances performance. Previous experimental studies suggested that applying an electric field broadens the parameter window for achieving desired morphologies and can produce longer cylindrical domains at the film surface. However, the detailed mechanism of this effect on the kinetics and alignment during evaporation remains unclear. To address this, the authors apply a soft, highly coarse-grained particle-based simulation model to capture the complex interplay of solvent evaporation, polymer microphase separation, and the influence of an electric field. They simulate a thin film of asymmetric AB diblock copolymer solution confined vertically between impenetrable electrodes, which also create a homogeneous electric field perpendicular to the film surface. Evaporation is mimicked by converting solvent particles to gas particles at the top of the simulation box, creating a solvent density gradient that drives ordering. This combined approach enables the authors to examine how electric fields control domain alignment and growth within evaporating thin films, revealing mechanisms behind experimentally observed effects. The resulting insights provide a deeper understanding of how processing parameters can be tuned to engineer nanostructures in copolymer films. Figure 1 illustrates the simulation box used for the evaporation-induced self-assembly simulations. The box is confined at the top and bottom by electrodes depicted in orange, which serve as impenetrable walls, as well as sources of a homogeneous external electric field, oriented perpendicular to the film surface. This boundary setup mimics experimental conditions, where electrodes apply electric fields across thin films. The topmost region of the box, colored pink in the illustration, represents the conversion zone in which solvent particles are regularly converted into gas particles, effectively modeling the solvent evaporation process. This dynamic reduction of solvent concentration creates a gradient that drives microphase separation within the film. Periodic boundary conditions in the lateral directions ensure a representative thin film environment without edge effects. This simulation geometry allows the study of how the applied electric field and solvent evaporation dynamically influence the morphology of the diblock copolymer film, including domain alignment and growth kinetics. The authors interpret this setup as enabling the investigation of the dielectrophoretic aligning effect, where interfaces between domains of different permittivity orient along the electric field vector, lowering the system free energy. Overall, Figure 1 establishes the framework for the subsequent detailed simulations and analysis presented in the paper. Figure 2 compares the microstructural evolution in melt simulations of the diblock copolymer without and with the application of an electric field. Panel A presents density snapshots at selected simulation times, illustrating the morphology development. Without the electric field, lamellae form but remain non-uniformly oriented even after long simulation times, indicating slow kinetics and less ordered structural alignment. In contrast, the application of an electric field aligns the domain interfaces preferentially along the field direction, resulting in uniformly oriented lamellae. This observation confirms the dielectrophoretic aligning effect, whereby interfaces between blocks of different permittivities orient to reduce free energy in the field. Panel B shows the time evolution of the structure factor of the composition fluctuations, highlighting characteristic peaks that correspond to the formation of a lamellar structure. The positions of the first three multiples of the fundamental periodicity peak are marked, accentuating the clear lamellar ordering under electric field conditions. These results indicate that the external electric field not only promotes domain alignment, but also affects the kinetics of order formation by accelerating the establishment of lamellar periodicity. The authors interpret these findings as evidence that the electric field reduces the orientational disorder in the melt, thereby favoring phase transitions, such as from spheres to cylinders aligned along the field. This aligns with previous studies and supports the role of the electric field as a powerful processing parameter for tuning diblock copolymer morphologies. Figure 3 explores how an external electric field influences the final morphologies of Diblock copolymer films during solvent evaporation under varying evaporation rates. The figure presents simulation snapshots comparing two scenarios without an electric field, top row, and with an applied electric field of strength E0.06, bottom row, under fast and slow evaporation conditions evoked by different solvent-gas interaction parameters. In the absence of an electric field, fast evaporation yields perpendicularly aligned cylindrical domains near the film surface. Applying an electric field under fast evaporation conditions does not further improve alignment, but aids in defect removal, facilitating better morphological order. However, during slow evaporation, without electric field application, a mixture of orientations emerges, with cylinders primarily aligning parallel to the film surface. This parallel alignment arises due to the slower growth kinetics and the formation of a minority block layer near the surface, which favors parallel configurations. When the electric field is applied under slow evaporation conditions, the dielectrophoretic force overcomes these competing factors, producing a morphology with exclusively perpendicularly aligned cylinders. The authors interpret these results as demonstrating the critical role of electric fields in controlling domain orientation by competing with solvent density gradients and surface enrichment effects. Thus, the electric field extends the processing conditions that yield desired perpendicular cylinder orientation during dynamic solvent evaporation. This work thus illustrates how the interplay between evaporation kinetics and electric field strength governs the self-assembled nanostructure in thin copolymer films. Figure 4 examines the influence of external electric fields on the one-dimensional density profiles of the minority block near the film surface for a system that normally exhibits parallel cylinders at slow evaporation conditions with a solvent-gas interaction parameter of 40. The plots show how the minority block density peaks change during structure formation at a fixed time point, comparing different electric field strengths. Without applying an electric field, a pronounced density peak of the minority block occurs close to the surface, indicating formation of a surface enrichment layer. This layer causes composition oscillations in the copolymer solution that promote a parallel cylinder orientation. The presence of this layer is energetically unfavorable when an electric field is applied perpendicular to the film, as the domain interface between this layer and the bulk is perpendicular to the field, destabilizing this configuration. As a result, applying an electric field notably reduces the amplitude of this surface density peak in a nonlinear manner consistent with the known quadratic dependence of the dielectrophoretic force on the field strength. These results imply that the electric field disrupts the formation of the surface minority block layer responsible for parallel cylinder orientation, thereby favoring perpendicular cylinder alignment. The authors interpret the dielectrophoretic force as providing a dominant contribution to domain alignment by altering the balance between surface enrichment effects and solvent evaporation-driven gradients. Additionally, the local polymer density thresholds for order-disorder and order-order transitions shift under the electric field, further promoting the faster growth of cylindrical domain thickness LCYL compared to the case without an electric field. Consequently, the electric field expands the parameter space conducive to perpendicular cylinder orientation by suppressing parallel layers at the surface. Figure 5 presents one-dimensional density profiles from solvent evaporation simulations, highlighting how the application of an electric field affects the growth and extent of the cylindrical domain layer, L-SIL, at a time t equal to 65 characteristic relaxation times. The plots compare data from simulations without an electric field, top gray lines, and with a moderate electric field of strength 0.05, bottom blue lines. Solid, dashed, and dotted lines represent the minority block A, majority block B, and total polymer density respectively. Regions corresponding to spherical and cylindrical microdomains are highlighted in green and red. Without an electric field, the polymer density profile exhibits an extended spherical layer with a thinner cylindrical layer above. The presence of an electric field leads to a distinct increase in the thickness of the cylindrical layer, while the spherical layer size remains relatively unchanged. This observation indicates that the electric field primarily shifts the polymer density thresholds related to the order-order transition, promoting elongated cylindrical domain growth at the expense of spherical domains. The authors note that this increased cylindrical layer thickness results from the reduction of the polymer density at the order-order transition, enabling cylinders to appear earlier and grow faster during solvent evaporation. Furthermore, this system features a shallow composition gradient, providing a conducive environment for observing significant changes in domain size induced by the field. In summary, Figure 5 illustrates that electric fields enhance the growth of perpendicularly aligned cylindrical microdomains by shifting the thermodynamic and kinetic conditions during evaporation, corroborating previous experimental findings, and supporting the theoretical model of dielectrophoretic alignment. Figure 6 depicts the temporal evolution of spherical and cylindrical layers during solvent evaporation of the Diblock copolymer system A7B25, comparing scenarios without A and with B an applied electric field of strength 0.05. The left panels present layer growth plots, where the thicknesses L-SPH and L-Sil of spherical and cylindrical domains, respectively, are measured with respect to the gas-liquid interface at position Z equals 0. Without an electric field, cylindrical regions emerge later, around 15 relaxation times after application of the field in the comparison case, and grow more slowly. The difference between cylindrical and spherical layer sizes increases over time, indicating expanding regions suitable for spheres, which is consistent with the observation of stacked layers of spheres beneath cylinders. Snapshot images in this case reveal meandering, fluctuating cylinders with irregular shapes and orientations. In contrast, when the electric field is applied, the cylindrical domains appear earlier, grow faster, and maintain a nearly constant gap with the spherical layer thickness, effectively suppressing formation of multiple spherical layers. Snapshots show perfectly straight, perpendicularly aligned cylinders, growing continuously from a single layer of spherical microdomains by elongation, with no observation of order-order transitions from stacked spheres to cylinders. The authors interpret these findings as demonstrating the kinetic advantage provided by the dielectrophoretic aligning force, which stabilizes perpendicular cylinders during evaporation and prevents orientation switching to parallel cylinders deeper in the film. These simulation results corroborate experimental observations where electric fields promote longer cylindrical domains aligned normal to the film surface, confirming the broadening of the processing parameter window for desired microstructures. Overall, Figure 6 highlights the dynamic influence of electric fields on self-assembly kinetics and domain morphology in evaporating Diblock copolymer films. In conclusion, this study elucidates how external electric fields act as a powerful processing parameter to influence the self-assembly and morphology evolution of Diblock copolymer thin films during solvent evaporation. By implementing coarse-grained particle-based simulations with electrodes generating homogeneous electric fields perpendicular to the film, the authors demonstrated that electric fields strongly promote the alignment of cylindrical microdomains along the field direction. This aligning effect arises from the dielectrophoretic force, which lowers the free energy by orienting interfaces between copolymer blocks with different permittivities parallel to the field vector. The electric field not only improves domain alignment, but also accelerates the growth kinetics of cylindrical domains by shifting the order-order transition to lower polymer densities. During solvent evaporation, this results in earlier onset and enhanced growth of perpendicularly aligned cylinders, while suppressing the formation of parallel cylinders and stacked spherical layers. These findings corroborate and rationalize previously reported experimental observations of broader parameter windows for achieving perpendicular cylinder morphologies under electric fields and longer cylindrical domains at the film surface. Additionally, the simulations reveal that the electric field stabilizes straight, defect-free cylinders by overcoming competing effects from surface enrichment layers and evaporation-driven concentration gradients. Overall, this work provides a detailed mechanistic understanding of how electric fields control microphase separation kinetics and nanostructure in evaporating Diblock copolymer films. Such insights enable improved design and optimization of processing conditions for advanced functional polymer membranes and nanostructured films.